The topic of today's discussion will be the process of initialization of system in MD simulation. We started this series by discussing the most fundamental concept about the MD simulation cycle and looked at the general outline of this topic. Now we will move on to the details of each step of the simulation cycle. As explained in the first lecture of this series, assigning initial position and velocity to all atoms of the system is the first step of MD simulation. Now in this lecture we will add more points in this topic. Let us first talk about how we can add new positions to all atoms of the system. In practical sense, the position of all atoms in a solid are given by the crystal structure of that particular solid. This crystal structure is made up of repetitive unique arrangement of atoms called as the crystal lattice. Total of 14 lattice structures were seen and were collectively referred to as the Bravais lattice. All these lattice structures differ from each other by their shapes and angles between the faces and are represented as follows. Let us consider the simple cubic lattice here. The points at the corner are referred to as lattice sites. These are the locations where the atoms or molecules are present. For instance, let us consider a cube of copper metal. The cube is made from numerous copper atoms arranged in a simple cubic lattice. If we take a closer look at the lattice structure, we could see that each copper atom is located at the vertex of the cube, which we refer to as the lattice sites. Now we arrange numerous crystal lattice next to each other. We will get a larger cube, which we term as the crystal structure of copper. Therefore, crystal structure is made up of numerous crystal lattices and the shape of the crystal structure is same as that of constituent crystal lattices. Famous techniques such as X-ray crystallography, NMR, neutron diffraction and electron diffraction allows us to determine the crystal structure as well as the lattice structure. Using this information, one can easily determine the location of atoms in space. Therefore, to place atoms in space, we need to essentially begin by establishing the crystal lattice or crystal structure in space. It is important to note that concept of crystal structure applies only to solid state matter. If your matter is fluid, this concept do not apply, as fluids that take up any shape, like the shape of the container they are present in. Now suppose I want to study the behavior of copper at higher temperatures using MD simulations. My first step will be to provide an initial position to all atoms. As the copper is solid, I can assign these position by establishing a simple cubic lattice. Therefore, in case of solids, the initial position of atoms can be assigned by establishing their respective lattice structure in the simulation. But what if we want to simulate the behavior of liquid? How we can go about it? As we want to simulate the behavior of liquid and liquids do not have a defined shape, we cannot assign a defined lattice structure to it. So how can we assign initial position to its constituent atoms or molecules? The answer is, as solids have well-defined lattice structures and these can be used to assign initial positions, we will also treat the liquid as solid and assign it the lattice structure. But this lattice structure will only be present at the initial stages of simulation. As the simulation reaches the equilibrium, this crystal lattice will melt and convert to the liquid state. We will take an example to understand this. Consider that you want to measure the density of water at 25 degrees Celsius. and at this temperature water will be in the liquid state. Therefore, we cannot assign a lattice structure to it, but we can assign lattice structure to its solid form, that is ice. We will assign lattice structure of ice as the initial position to water molecules that we are simulating. And as the simulation will progress, it will eventually get converted to water, that is the liquid state, as the temperature increases and reaches 25 degrees Celsius, which will allow us to measure the desired property. So, the complete summary of this discussion states that whether you want to simulate solid or fluid, you first need to assign initial position, and for that you need to establish the lattice structure. In case of fluids, this lattice structure would melt and get converted into fluid as the simulation progresses and reaches the equilibrium. Whereas in case of solid, this will not melt as it would represent and exhibit a solid state behavior. I would like to add one more point to this discussion. In case of solids, the shape of crystal lattice is fixed. That means the copper lattice would only exist in a simple cubic lattice. But what shape should be assigned to the initial lattice that we make for liquid simulation? The answer to this question is that, as in case of liquids, any lattice structure that will be assigned will eventually get converted into liquid. Therefore, any lattice structure is suitable to assign to the liquid that you are simulating. Up until this point, we have seen the use of crystal lattice in assigning initial position to atoms. But there are certain conditions where you should avoid using the crystal lattice, exclusively in case of liquid simulations. Then you would ask me, how can I assign initial position to my liquid molecules? So let us consider the following situation. Suppose you want to simulate the behavior of water at 3 degrees Celsius. At this temperature, the water should be in a liquid state. Following the previously mentioned step, we first assign initial position to molecules by establishing crystal lattice, and then we would expect it to melt to get water molecules in a liquid state at equilibrium. But as the simulation progresses and reaches 3 degrees Celsius, the crystal lattice would not melt completely and would exist in a metastable state. That means the half solid and half liquid state. As we were expecting the water to be in a liquid state at this temperature, it would be in a semi-solid state. And if we pursue to measure the different properties of water at this temperature, we would be getting wrong values. Suppose we measure density, then we would not get the density of liquid water, that is around 1 gram per cubic centimeter. Instead, we would get the density of ice, which is quite less as compared to liquid water. So, how can we avoid this problem? The answer is really simple. In such cases, avoid making the crystal lattice. Then you might ask, how can we assign initial positions without making a crystal lattice? We would set up another simulation where we will follow all the steps carried out in this simulation, with the only difference being the equilibrium temperature will not be 3 degrees Celsius, but it would be set slightly higher, say suppose 25 degrees Celsius. This will allow the crystal lattice to melt completely into liquid water at equilibrium. And then we will run another simulation. This time temperature at the equilibrium will be set at 3 degrees Celsius. But we will use the well equilibrated liquid water system from our previous simulation directly as our starting point. We would then simulate to reach the temperature of 3 degrees Celsius. And in this simulation, the water will be in the liquid state. The summary of this complete discussion states that when you want to simulate your liquid at near its freezing point, avoid making crystal lattice, as it will not melt completely, thus establishing a semi-solid state or a metastable state. This problem can be avoided by taking a well-equilibrated liquid state as the initial position of atoms. This well-equilibrated liquid state can be obtained by running yet another simulation but at higher temperature and assigning the initial position of atoms using the crystal lattice for that particular simulation.